Okay, so we talked yesterday about simple harmonic motion. What is simple harmonic motion? Does anyone remember from yesterday? Something that exhibits simple harmonic motion as opposed to difficult harmonic motion? Oh, yeah, the spring thing. A weight attached to a spring as you put it in motion, neglecting all those forces, right, like gravity and wind resistance and phototropism and other things like that. This thing will continue to oscillate above and below its resting position indefinitely by the same amount. So that would exhibit simple harmonic motion, which means we can model its position using what type of equation? Sinusoid, right? Either sine or cosine. All right, let's look at example 1. The Ferris wheel, and it's capital F. Why is it capital F? It's capital wheel. Why is it capital wheel? Is it named after Mr. Ferris or Mr. Wheel, the Ferris wheel? I'll let you Google that. There is a right answer. It's one of the two, Mr. Wheel or Mr. Ferris. Anyway, the Ferris wheel at the Comal County Fair, which is named after Mr. Fair. Maybe it's Coach Fair. No, he spells it differently. Anyone ever ridden the Ferris wheel at the Comal County Fair? Yeah, you have. It's one of those romantic rides, yeah? Yeah. When you get up there to the top, you could actually see the roof of the library. You're like, oh, there's that Frisbee. Anyway, the Ferris wheel at the Comal County Fair is a 3-minute ride that takes its riders on a thrilling ride up to a maximum height of 105 feet and to a low point of 5 feet. Up to 105, down to 5. Up to 105, down to 5. Assuming that the Ferris wheel rotates at 6 revolutions per minute and that the rider starts his stopwatch immediately as the ride starts at its low point. Okay, we got a nerd on the ride. He gets on and he starts his stopwatch. Time to calibrate. Part A, sketch the graph of the rider's height above the ground, h, so we're given a name to his height, h, in feet as a function of time, t, in seconds since the rider started his stopwatch. Okay, so let's come down here and get it started. We're going to graph his height, h of t, which is going to be feet above ground. It's going to be feet above ground as a function of t, time, in seconds since the ride started. Okay, so let's see if we can kind of decipher the information. If we can get the graph generated, I think then we can write the equation pretty easily, which is really what we're after. Okay, so let's see. If we're measuring his height above ground, it said that it went up to a maximum height of 105 and to a low of 5. So we can already kind of label that on our y-axis. We got 5 as a low point, and I'm just going to call that 105 up there. So maybe it's not drawn to scale, but I'm not going to draw the y-axis too terribly high. Now, from the warm-up, we saw that when I have the high and low point, that means that I can bisect that on my graph, and I can find the value of it very, very quickly by finding the average of those two numbers. How do we find the average of two numbers? Add them and divide by 2. So 105 plus 5 is 110. Half of 110, 55. Now 55 is going to be an important value because that is the center line. Maybe I don't put dots over there. That's going to be the what axis? Sinusoidal axis, which in our equation then, it's going to be which letter, A, B, C, or D? D. Good. So let's go ahead and start collecting stuff over here. We know the D value is 55. From there, we can figure out what the amplitude is. What's the amplitude? It's got to be 50, right? It's the distance from 55 to 5 or to 105, which is the same. It's 50. Now, what does 50 feet correspond to in terms of the Ferris wheel? It's it's the radius. Good. 50 ends up being the radius of the Ferris wheel. Okay, it's the amplitude. So that takes care of the vertical stuff. Now the horizontal stuff is always the fun part. In this case, we're measuring t on the y-axis, and here's t equals 0. It says that the guy starts his stopwatch at a low point, which makes sense. He gets on at the low point. It's hard to get on the Ferris wheel at the high point, right? You have to do a little climbing. So there's a ramp that leads up to it, and he gets on right there, and he starts it at a low point. And from there, we can assume then that the ride starts, and it goes up and down for 3 whole minutes. Wow, get me off this thing. I need to start then putting some marks down. I need to know the what in order to sketch the graph of the Ferris wheel. The speed? Well, I think there was a speed given. It said it rotates at 6 revolutions per minute. That's 6 RPMs. What kind of velocity or speed is that? Not a linear. That's rotational. That's angular velocity, which we use the W, which is not a W. Actually, it's a omega. So that's an angular velocity. How can I use the angular velocity to help me get the period? The period is the length of one cycle, right? But notice we have feet measured on the y-axis and seconds measured on the x-axis. So when we say the length of one cycle, we're talking about whatever the x measurement is. And so we're talking about how many seconds does it take to make one cycle or one revolution. Cycle and revolution are the same, right? One cycle, one revolution. So I want to know how many seconds it takes to make one revolution. That's the period. Well, if I know that it makes 6 revolutions per 1 minute, how can I use that to figure out how many seconds are in one revolution? Stoichiometry. Yeah, I can actually convert it. If I just flip the angular velocity, I'm going to get units of minutes per revolution. Yes? Which is a type of wavelength or period. So the omega, the angular velocity, and the wavelength of the period are really reciprocals of each other. So if I flip that, I get 6 revolutions down here and 1 minute in the top. But of course, if we don't want to use stoichiometry, we know how many seconds are in a minute. What's the answer? 60. Yeah. So you could say that 6 revolutions per 1 minute is the same as 6 revolutions per 60 seconds. And then if you flip that, you get 60 seconds per 6 revolutions. And of course, that simplifies to what? 10 seconds per 1 revolution. And if you can get that right there, some amount of time per 1 revolution, you have your period. It's 10 seconds. So it takes 10 seconds for this thing to make 1 revolution. Now this one is actually pretty intuitive. You might have been able to figure that out. If it makes 6 full revolutions every minute, that means it's going to make 1 revolution every 1/6 of a minute, which is every 10 seconds. So it might be intuitive, but this is how you can always do it. The reciprocal of your angular velocity is going to give you some version of the period or the wavelength, and then you just need to make sure that the units match up. So now that we have the period, the wavelength, we can actually put some values down. Now he starts at a low point, which makes it real easy. So I know that 10 seconds later, which I'm going to come out to about right here, I'm going to call that 10 seconds later, he has returned to his low point of 5. So from there, I can kind of work backwards like we've been doing. Half of 10 would be 5. Half of 5 is 2.5. What's the importance of 2.5? That's your quarter cycle counting interval. Every 2.5 seconds, this rider is going to go from a low point to a midpoint, an axis point, to a high point. So now you can label the midpoint there. 5 plus 2.5 is 7.5. And once you have that, you can now extend your marks all the way to as far as you've extended your graph. So just kind of keep the marks spaced about the same. You don't have to sketch the whole ride. Just a couple of cycles would work. And so now that we have those drawn, we'll label them. We'll just add 2.5. So we get 12.5, and then we get 15, and 17.5, and then we get 20, and 22.5, so on and so forth. Now, once you have those, you can put your critical values. So we have a low point, we have an axis point, we have a high point, we have an axis point. There's the low, axis, high, axis, low, and then I have one more there on the axis. And we connect them with these quarter cycle arcs, kind of exaggerating the curvature. Now I'm going to extend it on the right-hand side, but I'm not going to extend it on the left-hand side, because the sinusoid itself has a domain of what? Just in general, yeah, all real numbers, right? But when we have a word problem, we have what's called a relevant domain. We're using a sinusoidal equation to model a real-world behavior, but in the real world, all values might not be relevant. So our relevant domain is going to be all values of t that are between what and what? 0 and 3 minutes. We're measuring our t-axis in seconds, so 3 minutes is how many seconds? 180, yeah. So I might ask you for a relevant domain. The domain of the function is all real numbers, but we're talking about seconds on a 3-minute ride. So now notice this is kind of interesting. Because we're measuring the sine ratio or the cosine ratio on the y-axis, what are the units of the sine and cosine ratios? Remember, we're talking about like either the height or the width of a triangle on the unit circle. We would measure them in the same units, right? Sine would be like vertical to hypotenuse, so we would be measuring feet to feet. What happens when you take the ratio of feet to feet or inches to inches? They divide out. So all of the trig ratios have no units. They're ratios, the units divide out. We are measuring our angles on the x-axis in what? Degrees or radians? Radians, right? What are the units of radians? They don't have units. So because we are using ratios which have no units on the y-axis and radians which have no units on the x-axis, this is why we can model real-world behavior and assign any units we want to both the x and y axis. If you were to measure your graph in degrees, you would have degrees on the t-axis, not seconds, and it wouldn't work. So that's why we use radians. Okay, now that we have the graph, that we've answered part A, we need part B. Assuming that h is a sinusoidal function of time t, write a particular equation. Confirm it by graphing it in the graphing calculator. Okay. Let's go ahead and write an equation. Pretty easy now that we have the graph. It gave us the name of the function, so we can't call it y or f. We're calling it what? H of t. So if it gives you the name, use the name. H of t, his height in feet above ground, is going to be what? What's the amplitude? 50. Yeah, now you have the choice of making it positive or negative. You might as well make it positive, right? You have all the critical values for a full cycle at least labeled, so you could choose whatever you want. Hey, speaking of choosing whatever you want, you like sine or cosine better? Sahala or chala? You like sine? Okay. So 50 sine of. Now what goes next? 10 or 6 or neither? The b value goes next. We have the angular velocity is 6. We have the period is 10. Is that what goes next? No. We have to find the b value. The b value, remember, is 2 pi over the period, which is 2 pi tenths or pi fifths. Yeah. So we get pi fifths, parentheses, not x, but what is our independent variable? T. And then I'm going to leave it blank there, close, and then plus what for our d value? 55. Now, because y'all chose a positive sign, y'all need to get over to the place where positive sign would start, which is where? On an axis, high or low? Axis going up or down? Going up. Where's the axis going up point? We have several drawn there. 2.5 is probably the easiest. It's the closest one. So t minus 2.5. You could, of course, said minus 12.5, minus 22.5. They all would have worked. If you wanted to do a function without a phase shift, could we do that? Yeah, because he starts at a low point if we didn't want a phase shift, which makes the equation just a little bit more user-friendly. What would it be? Sine, cosine, plus or minus? No, it is cosine. That's right. Negative cosine. When you yawn mid-sentence, that doesn't show boredom, right? No. Okay, good. I don't take offense to that. That means you're oxygenating your brain, which means you're ready for the next problem, which means you might be bored. Negative 50 cosine of pi fifths. I don't need the extra parentheses for the phase shift. I just put the t there. Close plus 55. So which one of those is correct? They both are. Yeah. In fact, let's confirm that on our graphing calculator. If you would like to come up now and grab a graphing calculator while I load mine up here, that would be fine. We're going to be using the graphing calculator in this section, so you can kind of grab one over the next few days as you come into class if you don't have one yourself. Simply because we're going to be computing these sine and cosine values at like funky numbers where the decimals are not on the unit circle. All right, go ahead with your calculator and make sure it's in what mode? Radian. And go to Y1 and type in one of the equations, and might as well go to Y2 and type in the other one we wrote. And if they are, in fact, the same, we shouldn't see a difference between them. So I am in radian mode. Get rid of that x squared clutter. 50 sine of pi fifths. Notice it opens the parentheses. If you don't want to use the horizontal bar, pi divided by 5 is fine because it's just two factors. Open. We always use x on the calculator, even though we're calling it t. Close it for the shift. Close it for the angle. You have to have double close right there. Plus 55. All right, that one's going to be in blue. I'm going to go down here in this one and type in negative 50 cosine of pi fifths. Don't need the extra parentheses. Just put x, close, plus 55. Now, yeah, go ahead. Plus 5? I don't know. Look at our equation. If we went plus 5, that means when we come back down 50 from 5, we're going to be 45 feet underground. Our legs are going to scrape. Yeah. The sinusoidal axis is up at 55. 5 is the low point. Now, since we've already thought it out and graphed it on our iPad/paper, let's go ahead and go to the window. You don't hit zoom 6. You've already thought it out. So let's let our x min, which is time, be 0. Let's go ahead and sketch it for the full ride, huh? Might as well. How many seconds is that? 180, good. Now, when you go from 0 to 180, you don't want to put a tick mark on the x-axis, so go ahead and set your x scale to 0. Y min, what does the x-axis represent in this problem? Does it have any relevance? The x-axis. We're measuring time, but if you're measuring the distance above ground, then the x-axis itself could represent the ground itself, right? Yeah. So let's go ahead and do this. I'm going to set this to negative 5 instead of 0, just so I can see the x-axis. And then my y max, 105 is our high point, but let's go a little bit above that so we can have some buffering space up there. So maybe 120 or something like that. And we'll turn our y scale to 0 as well. Now, when you hit graph, you should see a very nice picture. Here we go. It should look very similar to what we did. Yay, we're going up. Uh-oh. Does y'all's look like that? Uh-oh, here's my other one. Oh, they don't appear to be the same. That's two different rides. Yeah, very good. If you have already thought out the problem and you have put your scale down on your paper and you've typed them into your calculator and you've double checked and you've set it in a window that matches your paper and you hit graph, if you don't see what you're expecting to see, you need to learn to troubleshoot. Because on a test, if you don't troubleshoot, you're going to get all the wrong answers on a free response, right? So troubleshooting. Someone said maybe I'm what? I'm in degree mode. You might have seen me switch back. But that would be like the number one mistake that students make. Because if you're in a physics class, maybe you're in degree mode. If you have your own calculator and you come back over here without checking, this would be a big problem. And here's another visual proof that degrees and radians aren't the same. If you check that you're in radian mode, now you hit graph, you should see what you expect. Whoa, look, we're on the Ferris wheel. Whoa, we're going up, going down, going up, going down, going up, going down, going up, going down. Maybe 3 minutes is a little too long for this ride. Oh, there's the frisbee, there's the frisbee, there's the frisbee, there's the frisbee, there's the frisbee. Oh, and here comes the next one. Notice it's tracing right on top of the other one. That's pretty cool. Looks like a sewing machine stitching right on top of the other one. Now it's red. Now that's visual confirmation that the two equations are the same. But could it be that they are not the same still? It's just tracing over really close to the other one? What could you do to validate it very quickly that they are in fact the same? If you go to the table of values, it'll generate, it's set up by default to generate random values. If you compare the columns, notice the y values for both of them appear to be the same. And if you scroll into the column, I don't know if you've noticed that, but if you scroll into the column and highlight one of the numbers, it gives you more of the decimals down below. So it's showing 0.451, but it's really 4508. So it's rounding. And if you click over to the right, you'll see that the decimals are the same all the way out. So there's some numeric confirmation that they are the same. And of course, we know that they actually are the same. Okay, so cool. Now that we have an equation in there, I'm going to go ahead and turn this one off because I don't like red. I like blue. All right, so there's the blue graph. So while it's graphing, let's come back to our work over here. And now that we know that we have the right equation and the right graph, we can now use our equation to answer some questions. Part C, how high above the ground is the rider at 48.5 seconds? At this time, is the rider going up or going down? Pretty easy question now. If you want to just eyeball it, come over to your graph. Did our graph that we generated go out to 48.5? No. So here's what you're going to do. You're going to have to show me, if this were like a free response or a quiz, what you're plugging into your calculator. There's a little bit extra burden of notation when you use your calculator. You can't just use it and write an answer down. So 48.5, is that an input, a t value, or an output, an h value? Input. So remember, in function notation, you would write h of 48.5. And that's all you have to write, h of 48.5. Now, there's two ways to do it. If you do it from the graphing screen, because you have the entire thing there, all you have to do is hit the trace button, and it'll put your cursor there. You can actually type right over it. It will accept an input in trace mode. And when you hit enter, you'll get a blinking confirmation of that. So notice it says 25.610737. How many decimals are you responsible for reporting? 3. So if you truncate, do you need that third zero? Or the zero in the third decimal place? Yes, you do. So I'm a fan of truncating, 25.610 feet. But if you want to round, 611 feet works as well. Now, what's nice about doing it from the graphing screen is you get a visual confirmation of where it's at. At that point, he's 25.610 feet above ground, heading what? Up or down? Heading down. Okay? So you would write that on your paper. Here is your numeric answer. So you could say at 48.5 seconds, comma, the rider is 25.610 feet above ground. I guess he's above ground the whole time, heading down. So I'm going to have you write these sentences. When you get into calculus, you'll be writing these sentences in the same format pretty much all the time. Let me show you the recipe for this sentence. You start with an introductory adverbial clause that references the moment in time. Got it? You start with an introductory adverbial clause that references the moment in time with units. So in this case, at 48.5 seconds, comma, and then you give your description. The rider is 25.610 feet above ground, heading down. That answers it. So you have two different answers now. You have a numeric answer, which is up here, and then you have your verbal answer. And you're going to have to always represent both. On any final numeric answer, make sure you put your units, and any verbal answer, make sure you put your units on both your independent variable, which is why we start with that introductory adverbial clause, and your dependent variable, which is feet. Okay? Now, why do we have to write both of them? Well, because the sentence is very nice because it summarizes. It's kind of like the old game, Who Wants to Be a Millionaire? Like, is that your final answer? That's my final answer. You're declaring it. It takes a little bit more effort. But we're going to work problems soon enough where you're actually going to have a negative value here. And if you have a negative value, it's like a vector. You're going to have to interpret if you're above something or below something. So you're going to have to interpret the sign and the quantity itself, the magnitude, as two separate things. Okay? Any questions on that? Too easy? Too much fun? Are we taking all the fun out of the Ferris wheel ride? Overanalyzing it? Like, yeah, let's go to the zipper now. Okay, we're almost done. Part D, at what positive time? Oh, by the way, let me show you another way to do this. Let me show you one other way to do this. Let's say that you didn't want to graph it all the way out to 48.5. I think I've showed you this before. From the home screen, you can compute function values without getting the visual. You just have to recall the y where you have your function. We put it in y1, right? So if you go alpha trace, which is your shortcut to your y's, there's y1. If you open the parentheses and plug in a 48.5, close parentheses, it'll accept that as function notation. So you can hit enter, and you get the same number. So you get where he is, but what's the downside possibly of doing it this way? The follow-up question was, at this moment, is he heading up or down? That number gives you a snapshot. It doesn't tell you what's happening before and after. So how could we then use data, numbers, to determine if he's going up or down at that moment? Come on, finding that information is dependent upon us getting off this island and getting on with the rest of our life.
You could plug in a bigger value, like 49, and see if it's going down.
Perfect. Let's see what's happening in the very near future, right? And compare it to this number. Now, you said 49, which is a half second away. That's not a bad idea. But what could happen in that half second? He could actually be turning a corner, and you can get misleading information. So I like the idea of looking into the future, but let's look into the future not so far. How about 48.6? That would be a tenth of a second, or 5.1, right? That would be a hundredth of a second. The closer you can have it to the value that you're interested in, the less likely you're going to be turning a corner and getting wrong information. So notice only a tenth second later, it's already 2 units smaller. So that's an indication that he's heading what? Down. Yeah. So as a rule of thumb, here's what I would recommend. Instead of actually going a tenth of a second, if it were a 5, that's what it was, just go ahead and add like an 0.1 to the end of it. That would be a hundredth of a second later. And now you compare 25.6 to 25.5, and you could see a hundredth of a second later, he's a tenth of a foot below. That's probably a safe thing to do. Now you can see that he's going down. So this might be useful because I'm going to ask you questions where you're graphing it from like 0 to 100, and I might be asking you what's the value way out here at like 5,000. And you don't want to have to like re-graph it and set your window and wait for it to graph. You can just do it this way. This would be a numeric analysis, flying by instrumentation only. Sure, it's fun to see it graph and then see the blinking thing right there, right? Ooh, there he is. But this is a little bit more efficient. Okay, that's part C. Let's look at part D. At what positive time is the rider 88 feet above ground and coming down for the third time? Ooh, 88 feet above ground, coming down for the third time. Well, how am I going to do that? Is 88 feet a time value or an h value? H value. So here's what you would show me on your quiz/test. You would say h of t equals 88. We did a lot of this when we did the logistics, like the Wurst-Fest logistic equation. H of t equals 88. And then underneath there you would say t equals whatever. Now how do we solve if we have a y value? You have two options. You can manually set this equation equal to 88 and then solve for t by dividing by a negative 50, taking the inverse cosine of both sides, yucky, yucky, gross, gross. Or, what did we do when we studied logistics? What can I do with the 88 since it's another y value? You can graph it. This is where the graph is helpful. If you actually graph the other y value, you now get a visual. So this is where the graph is helpful. You got a nice visual. Every time the blue graph intersects the red graph, the rider is at 88 feet above ground. So now you have to read carefully the description. We want to know where he's 88 feet above ground, coming down for the third time. Okay, let's see. So the second intersection is where he's coming down for the first time. The fourth intersection is where he's coming down for the second time. So it's the sixth point of intersection where he's coming down for the third time. You'll see that? So how do we find points of intersection on the calculator? Second trace, number 5. Now it's going to say, is this the first curve? Yep, that's a good one. Hit enter. Is this the second curve? Yep, it's not really a curve, but okay, stupid calculator. It's kind of straight, not curvy at all. And then for the guess, this is where the guess matters, right? If you're not scrolling close to the point you want, it might give you the wrong one. Now you can use symmetry to help you find one, but we know exactly where it's at. So let's go ahead and just scroll over to the sixth point of intersection, which would be right about there. Okay. When you claim your functions, you don't have to be near it. So notice I just hit enter for identifying the two curves. But when it's time to guess, that's where you scroll pretty close and hit enter. And you get a nice confirmation there that it's at 26.352. And what are the units? Seconds. Yeah. So in this case, I probably wouldn't make you write a sentence because it's pretty easy. But you would say, if I did have you write one, at 26.352 seconds, comma, the rider is 88 feet above ground, coming down for the third time. All right, h of t equals 88, bless you. You put units on your final numeric answer. That happens when t equals that. So once again, we're using our calculator two ways. I either give you an input, which means you plug in a t value, you hit the trace, or you go to the home screen, or I give you a y value, and you're graphing it and finding a point of intersection. God, how much more do we have on this problem? Oh, E, I love this question. During the 3-minute ride, for how many total seconds was the rider above 100 feet? Well, that's kind of interesting. Show the work that leads to your answer. That means if you just have the correct answer showing up, you're getting how many points? None. All right. So here's what we want to know. We want to know for how many seconds was the height greater than 100. That's the inequality we're trying to solve. So let's see. How would you go about solving that? Would you wait till the rider got off the ride and then ask him, hey, dude, how long were you above 100? It's like, I don't know. I was looking at Frisbees. Good. Set y equal to 100. Let's do that first, and then you can continue your explanation. So there it is. We're writing it again. Yay, go us. And then we're going to see that line come in at 100. Then what would we do? The entire ride. The tip? Like the high point? We need to find the points of intersections, right? These are all, they don't look symmetrical because the calculator is trying to crunch them in there, but what do you know about the symmetry of the sine wave? They're all the same, okay? So all we have to do is figure out where it intersects on the way up and the next point of intersection immediately coming down, and then subtract those two, right? And that'll give us the distance that's above 100 on each trip around. And then we just have to figure out how many times it did that, right? How many times were we above 100? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Take a break. 11, 12, 13, 14, 15, 16, 17. Take a break. Crap, where was I? I forgot. So, okay, good. Don't take too long of a break. 18. So we were above 100 on 18 cycles. So all we have to do is say, okay, there's 18 cycles, and then figure out what the points of intersection are. So let's go ahead and go second trace, number 5, and enter, enter. Now, it doesn't matter which ones we use. So I'm going to go ahead, since I'm close to, my calculator's frozen. Oh, that's wonderful. It's always great for demonstration purposes. You just need to find 2 consecutive points of intersection between one going up and one going down. So let me come over here and let me find this one here.